More than 370 lunar meteorites have been collected on Earth, representing more than 30 different meteorite finds, no falls, with a total mass of over 1,090 kilograms, 2,400 pounds. Some were discovered by scientific teams, such as ANSMET, searching for meteorites in Antarctica, with most of the remainder discovered by collectors in the desert regions of northern Africa and Oman. A moon rock known as NWA 12691, which weighs 13.5 kilograms, 30 pounds, was found in the Sahara Desert at the Algerian and Mauritanian borders in January 2017, and went on sale for $2.5 million in 2020. Almost all lunar rocks are depleted in volatiles and are completely lacking in hydrated minerals common in Earth rocks. In some regards, lunar rocks are closely related to Earth's rocks in their isotopic composition of the element oxygen. The Apollo moon rocks were collected using a variety of tools, including hammers, rakes, scoops, tongs, and core tubes. Most were photographed prior to collection to record the condition in which they were found. They were placed inside sample bags and then a special environmental sample container for return to the Earth to protect them from contamination. In contrast to the Earth, large portions of the lunar crust appear to be composed of rocks with high concentrations of the mineral anorthite. The mare basalts have relatively high iron values. Furthermore, some of the mare basalts have very high levels of titanium, in the form of ilmenite. Lunar granites are relatively rare rocks that include diorites, monzodiorites, and granophyres. They consist of quartz, plagioclase, orthoclase or alkali feldspar, rare mafics, pyroxene, and rare zircon. The alkali feldspar may have unusual compositions unlike any terrestrial feldspar, and they are often bar-rich. These rocks apparently form by the extreme fractional crystallization of magnesian sweet or alkali sweet magmas, although liquid immiscibility may also play a role. UPB date of zircons from these rocks and from lunar soils have ages of 4.1 to 4.4 Ga, more or less the same as the magnesian sweet and alkali sweet rocks. In the 1960s, NASA researcher John A. O'Keefe and others linked lunar granites with tektites found on Earth, although many researchers refuted these claims. According to one study, a portion of lunar sample 12013 has a chemistry that closely resembles javanite tektites found on Earth. Lunar breccias range from glassy vitrifier melt rocks, to glass-rich breccia, to regolith breccias. The vitrifiers are dominantly glassy rocks that represent impact melt sheets that fill large impact structures. They contain few clasts of the target lithology, which is largely melted by the impact. Glassy breccias form from impact melt that exit the crater and entrain large volumes of crushed, but not melted, ejecta. It may contain abundant clasts that reflect the range of lithologies in the target region, sitting in a matrix of mineral fragments plus glass that welds it all together. Some of the clasts in these breccias are pieces of older breccias, documenting a repeated history of impact brecciation, cooling, and impact. Regolith breccias resemble the glassy breccias, but have little or no glass, melt, to weld them together. As noted above, the basin-forming impacts responsible for these breccias predate almost all mare basalt volcanism, so clasts of mare basalt are very rare. When found, these clasts represent the earliest phase of mare basalt volcanism preserved.